Welcome to another video on complex numbers. Last video was a historical look at the very first usage of complex numbers by Cardano in his book Ars Magna. Today what we're going to do is look at how our number systems have been built up in modern mathematics, because number systems are the building blocks, the scaffold that holds up the rest of modern mathematics. So it's very important that we understand what a number system is and how we can build it up. And that's what we're going to do today. We're going to start from the simplest of number systems and slowly build them up. Before we do that, we need to do a review of some advanced and some extension 1 maths on sets, just to make sure we have a concrete understanding of them, because essentially they're the building blocks, or part of the building block of a number system, along with one extra little piece. So let's jump into it. A set is just a collection of objects. It doesn't matter what order those objects are within the set, and it doesn't matter how many times that object appears in the set. All we care about is that there's some distinct objects in the set. That's the set. The way I like to think of it is, if I went to Woolies and then I went to Coles and I bought a bag of Skittles from each, those two bags of Skittles, as long as I bought the same type of Skittles and not a special edition bag or something like that, those two types of bags should be exactly the same in terms of they've both got Skittles in them. They're the same colors, but I don't care how many of each color is in the bag, and I don't care what order I pour the Skittles out of the bag. All that matters is if I pour the Woolies bag into one bowl and the Coles bag into another bowl, I'm going to have a bowl of Skittles. They're going to have the same colored Skittles in them. They're going to taste the same. That's what I mean by a set. It's just a collection of objects. It doesn't have to be numbers, as you saw. It could be Skittles in terms of their color. For us in maths, it normally is numbers. So let's look at some definitions and some nomenclature, some symbols that we use for sets. So when I'm talking about a set, I use a capital letter. So here I'm using S for set, and I use lowercase letters to represent those elements, those objects in a set. So here I'm saying X is an element of S. It's one of those objects in S. And I use this kind of E-looking symbol to represent that. That if I read that, it says X is in S. That's what that symbol means. If I want to say that something's not in S, then I just put a line through it, like a not equal sign. So here I would say Y is not in S. And we normally look at sets in terms of, or more abstract sets, in terms of what's called set roster notation. And we'll see that in a short while. Okay. So here's an example. I have 4 sets, A, B, C, and D, and I want to talk about which sets are really the same thing. Because remember I said I don't care what order the objects are in, and I don't care how many of those objects are in there, just what are the objects that are in there. Okay, so set A has the numbers 1, 2, and 3 in it. B has the numbers 2, 1, and 3. They're just the same things, they're just in a different order. So they're actually the same set. I don't care what order they're in. C has the numbers 1, 2, 3, 2, 1, 3, 3. It's the same 3 numbers again, 1, 2, and 3. I don't care that 3 occurs twice, and I don't care what order they're in. It's just got the numbers 1, 2, and 3 in it. D is different though. D has something that's not in the other ones, 1, 2, and 4. Or the other way of thinking, it has something missing, the number 3. So it's different. It's not the same set. Okay, so A, B, and C, they're the same set, but D is different. Okay, something called a subset. Now this wording here is not quite right. I need to update my notes, but I'll just talk over the top of it. So just note that's incorrect. When we're talking about a subset's just a smaller set that contains some or all of the elements in a bigger set. Can't contain anything else. It can only contain parts of or all of that bigger set. That's what we mean by a subset. And if it only contains some of, but not all of it, then it's called a proper subset. That'll probably be easier to understand when we look at the example. The symbolism that we use is this kind of C shape, and it's directional. So this says that A is a subset of B, not the other way around. Okay, so it's important that we have the direction. Here's an example. So I've got this set S, which contains 4 objects, 1, 2, 3, and 4, and we want to know which of the 4 other sets is a subset. Okay, so if I look at A has the number 1 in it, and that's it. And that's one of the elements in S. So it's a subset. It doesn't have anything else in it, just the number 1. So since it's part of S and it doesn't have anything else in it, that's a subset. B, again, just because it's got 2 number 2s, I don't care. It's got the numbers 1 and 2 in it, and that's it. Nothing else. And the numbers 1 and 2, they're in set S. So it's a subset. Set C has only exactly the same numbers as S, so it's also a subset. But this one is what we would call not a proper subset. So A and B, they're proper subsets because they contain part of S, but they don't contain everything in S, whereas C contains everything in S, so it's not a proper subset. And it's an important point that a set can be its own subset. D, though, is different again. D is the odd one out. D contains 1, that's in S, that's great, but the number 5 isn't in S, so it contains something that's not in S, therefore it's not a subset. Okay, so now we're going to talk about number systems, and they're kind of, like I said, the scaffold of modern mathematics. And the first type of number system, the simplest type of number system that you've dealt with in your schooling, is the natural numbers, and they're just the positive whole numbers. So the numbers 0, 1, 2, 3, all the way up to infinity, they're the natural numbers. And we use the symbol N for natural, but we can also call them the counting numbers or the cardinal numbers as well. And when we say number system though, yes, that's a set. That's the set 0, 1, 2, 3, 4, just a set of numbers and only the positive counting numbers. But a number system includes an operation as well. So we could have that set with addition, or that set with multiplication. So we take pairs or 3 of them or 4 of them, and we can add them and multiply them. That's a number system. Okay? And we can talk about number systems being closed. A number system being closed means that if I take that sum of that set, let's say the numbers 1 and 2, and the operation addition, so 1 and 2 add together to give me 3, if whenever I do that operation, I get a number that's in that set, that's what we mean by closed. Okay, so the natural numbers are closed under addition because it doesn't matter what numbers I take out of the set. If I add them, I'm always going to get a number that's in the set. Multiplication's the same, but they're not closed under subtraction or division. If I take 1 and 2 and I subtract them, I get -1. That's not in the set. Okay, so this idea of closure is kind of like in a video game. If you're running around the map, you shouldn't be able to fall through it. If it's closed, if it's not a buggy game, you should be able to run anywhere and not fall through the world. And I'm sure we've all experienced that, so they're not quite closed. Okay, that's what we mean by closure. You shouldn't be able to fall through the map. And if you can, it's not closed. Next is the integers. And to get the integers, which again we met in year 7, we only need to add one extra number, -1, to our set, and then with the operation of, say, subtraction, we can get all the other negative numbers as well, because I just keep subtracting 1, and then I get -2, -3, -4, -5, all the way to -infinity. So I just need to add that one extra number, and now the integers, which we use the symbol Z for, and I'll explain why in a minute, they become closed under not just addition and multiplication now, but they're now closed under subtraction as well, which is quite nice. And that Z, the reason we use the symbol Z and not I for integers is because it's actually, it represents the word number, but in German. Zahl or Zahlen is the word for number in German. And the reason we choose German is because these systems, or this number system is the simplest kind of mathematical object, which we call a ring. And we're not going to go into what a ring is, that's way beyond our course, but it's the simplest type of ring. And the mathematician that first developed the basic theory of rings was Emmy Noether. And Emmy Noether was a German mathematician, hence we now use the symbol Z to represent integers. Emmy Noether is a really competent mathematician. She's quite famous, not just in mathematics for ring theory, but also in physics, because she used that, she built up that mathematics of ring theory so that she could develop one of her theories in physics called the Noether theorem, which is all about symmetry and invariance, things that don't change and it's an important theory in cosmology and probably a few other fields as well. So she's quite a brilliant mathematician. Einstein thought of her as one of the most amazing mathematicians of the time. Okay, so that's where Z comes from anyway. We still can't close things under division at this point, which is an issue. So we need to extend our integers to include fractions so that we can do division, and we call these the rational numbers. Again, we don't use R here, we use Q for quotient to do with division. Okay, and here's our first demonstration of set-roster notation. So now we can describe what set-roster notation means. So it looks scary, but it's really easy to read. Basically, it's set up as a set, just like before, but instead of listing all the objects, we put a rule in there, and then we explain what that rule is. Okay, so Q, the rational numbers, is equal to, or is the set made up of objects P over Q, so they're a fraction, P over Q, and then we describe what P and Q are. P and Q are integers, so they're positive or negative whole numbers, but Q can't be 0. That's all that says. Okay, it's not scary. So now we've got all the integers, because 2 over 2, for instance, would just be 1, so we can still get the integers, but now we get fractions as well, which means we can do division. So this is the first of our number systems now that we've been building them up that's closed under all 4 basic operations. It's closed under addition, subtraction, multiplication, and division, and this is the simplest example of what we call a field. Okay, and you've probably heard that word field if you've done some science and some physics, gravitational field, magnetic field. That idea of a field, that physical concept of a field, has these things, these fields, these mathematical objects underneath them. So again, really important part of mathematics essentially is these number systems. Rings are important, fields are important. Okay, and I've said there, all fields are rings, but not all rings are fields. So again, this idea of directionality in mathematics is really important. Sometimes one direction is true, but not the other direction. And when we go through the topic of proof, we're going to talk about that a lot, okay? And we need to understand that concept. We still have a problem. Even though the rational numbers are a field, they're closed under all of the basic operations, they're still not quite enough. And that's what Cardano's first use of complex numbers was basically all about. He had a really simple problem that required the quadratic formula, and he didn't get any real answers popping out. He didn't get any answers popping out. So there was a problem. And same thing with the rational numbers as well. If I try and solve a problem like x squared plus 2, no, that's a bad one, x squared minus 2 equals 0, when I try and simplify that, I get x squared equals 2, and the answer is going to be positive or negative square root of 2. That's not a rational number. That's an irrational number. That's a surd. Okay, so we need to create these new numbers called the real numbers, which take into consideration those irrational numbers like surds or pi. So all of a sudden we can solve quadratic equations, we can solve cubic equations, we can solve trigonometric equations, but we still have that issue, that idea that sometimes even these numbers aren't enough. So we need to include this brand new number called I, the imaginary unit, where we just say I is equal to the square root of negative 1. And then I can build up this whole new huge world of what's called complex numbers. And that's what the rest of this topic is going to be about. What do these numbers look like? How can we work with them? How can we add them, subtract them, multiply them, divide them? How can we find powers of them? How can we use them to solve quadratic equations and polynomials?